So welcome everybody to this seminar. We want to welcome Dr. Chen, who is visiting us from the University of Kentucky, and he is a potential faculty recruit, and so has been meeting with many of us, both in nephrology, but I think also with you guys in the Informatics Institute. His research focuses on the development of artificial intelligence and machine learning tools to solve a wide variety of problems, of biomedical problems. And he's interested in analyzing unstructured data, such as longitudinal EHR data. As we were discussing this morning too, he helps a lot of basic scientists like myself with our omics data analysis and study designs and things like that. He is a tenured associate professor in biomedical informatics at the University of Kentucky. Let's see. He is a co-I or a PI on a large number of grants. There's 8 listed on his CV, and he is a co-I on a pending NIH R01. He has published a large number of peer-reviewed publications in top informatics and other journals. You have listed on your CV over 92 publications, so obviously you've been very productive over your career. He also has a patent and numerous teaching experiences. And so we welcome you to UAB today and very much look forward to your presentation on unbiased representation of clinical data for precision patient outcome predictions. Dr. Chen.
Thank you, Kelly, for the introduction. Let's start my presentation. So today I'll talk about unbiased representation of clinical data for precise patient outcome prediction. If you have any questions, you can just stop me. I will really appreciate your help. So we started with EHR data. Now, when I talk through these slides, I already know that some people will like it. Now, the EHR data is big. It's very detailed. Some people hate it. They say this EH data has lots of missing values and it hasn't been fully standardized. But nevertheless, the EH data is here. And over years, we see the data is getting bigger, the quality is getting higher. So we also witness a growing interest in mining this temporal multimodal EHR data to recognize some electrical data signatures or patterns that's shown associated with patient outcomes. It's open opportunity for develop accurate, personalized risk stratification tools. It can be incorporated into our clinical practice or ultimately realizes the precision medicine. So there's lots of potential out there about how this EH data can deliver. Well, if you look at the literature, you found that the comments are quite mixed. Some people said the data is rich, but the information that carried in the data is poor. And some said that this EHR data could introduce some bias. And I don't know if you remember that in the early stage of the COVID case, there's some high impact journal papers retracted because people have concerns about how the EHR data were handled. Do they really use the data on the right way? And besides the machine learning algorithms, although that it's kind of from another angle, we can't just use the data as is. There could be still potential bias that could be introduced by the model, by the data, or the combination of the two. Dr. Semino has been researching this EH data for a long time. He also has his opinion about we need to ask questions about the why in the EHR, how this can be used to fix the problems in current EHR system. Dr. Semino gave a talk at the UK in 2016, and we're all impressed by his opinions. But on the other side, you could see that the artificial intelligence has got lots of attention, especially the deep learning algorithms. There's lots of applications in areas like face recognition, natural language processing. They show greater contribution in the prediction of real-world problems. They have achieved a higher accuracy and more robustness and more efficient than traditional machine learning models. And the overall performance was pushed to the limit with the availability of a large volume of data. So deep learning algorithms are somehow we would consider particularly good in handling unstructured data, such as in our case, could be clinical notes, medical images, brain signals, and temporal EHR record. So we would think that it's a win-win when we put the EHR data and the deep learning algorithm together. We may use a power, when you need the rich information in the data and also the power of deep learning algorithms. But things are not that simple. When you look at the deep learning algorithm, you also see that sometimes we'll say that algorithm can be easily fooled. As a show example on the left side is a panda picture, which you can see the algorithm has a 57% confidence say it is a panda. And now we add some noise to it. The picture on the right side still look like a panda, but the algorithm, a deep learning algorithm would say this is given with more than 99% confidence. Of course, it may make some mistakes. So we don't want these mistakes happening in our EHR daily practice using EHR data. Some people also did this mimic data analysis. They look at the mimic 4 data set, which basically is the identified ICU data, and they want to see can we interpret the deep learning models? Can we achieve a high fairness while we apply deep learning models on this mimic 4 data set? What they found is surprising. They say this interpretability and the fairness are not contradicting each other. In fact, they help each other. The model that has high interpretability also have high fairness scores. So this gives us the idea that we will develop a deep learning algorithm to solve to address a clinical problem using EHR data. We somehow need to make some adjustment so that the model and the data can match with each other and deliver better results. So here, this is a diagram I just created. So on the left side is our EHR data. On the right side is the artificial intelligence. We're supposed to build a bridge to connect the two, but in the current status, the bridge is somehow still broken. And we realized that could be several problems that block the bridge. On the data side, it could be the concept, some concept in the EHR hasn't been standardized. We expect a lot of work on that end so that the data can be streamlined and can be understood by the model. There are lots of missing data in the model, in the EHR data, but the missing means something. That not simply because the data is missing. This missing could mean the patient has severe conditions or something haven't been documented by the current system. There could be bias in the data regarding gender, age, or other factors. On the computer side, the tool, the artificial intelligence tool we developed today, it's still pretty difficult to interpret the results. They are black box, and to find out why the machine made this decision is not straightforward. There could be data distribution shift problem, meaning that a model that trained and run very well on one data set can't be reused on a different data set or to address a different disease problem. The model fairness could be a problem because we expect that the model should have a similar performance on different patient subcohort. We don't want the model working well in general, but for a special minority group, the performance drops significantly. So all those problems are very interesting and they worth studying. So my lab build these problems, and then we choose a few cases and try to show that if we can make any progress. So the first take-home message I would like to say is that the EHR data volume and the quality improve really quickly these days. And this recent advance in artificial intelligence could be used to model EHR data towards precision medicine. I will use 2 projects in my lab to show what we have done in this direction. The first part of the talk will be focused on the disease outcome prediction for ICU AKI patients using the EHR-based data. The second part is about the imaging. So we try to standardize CT images for lung cancer patients for their outcome prediction. So let's start with the first one. Okay, many of you here are nephrologists, so I don't have to say anything about it. But in general, the AKI or acute kidney injury is a sudden decrease in kidney functions that happen within a few days or hours. It could cause a lot of burdens for the patients. The mortality rate for ICU patients with AKI is greater than 50%. A particular subgroup is called AKI requiring dialysis or AKID. They have an even higher risk of hospital mortality rate. So our first task here is to predict a kidney recovery of AKI patients. And this model, if it's successful, it can help to implement early and effective intervention and reduce the healthcare cost. Of course, this is just an example that we framed, and this we expect that the AI algorithm we developed for this program, for this specific problem, can be extended to other kidney disease problems. The current clinical approach are based on these three: Apache, SOFA, and the SAPS. They have been used. They have well proven. Have been used widely. The problem is that those tools for general ICU scoring system, they are not specifically designed for kidney disease. And they usually make a prediction at the end of treatment. Sometimes it was too late to get a score. So we wonder if we can use a deep learning algorithm, are we going to get a better performance? So the first thing we wanted to do is simply get the data ready and to see if there's anything, any pattern we can find without using any algorithm. So here is just a small cohort at UK with about less than 7,000 patients. And in the figure on the left side is this heat map, which just shows the pairwise similarity of these patients regarding their kidney scores. The hospital mortality is displayed next to the chart, so you can see there was a bar. And if there's a black bar, that means the patient died in ICU. And then you can see that this red boxes basically means the patient have a similar kidney scores. And particularly, you can see that this box and this box with almost equal size, but they are very different from each other regarding the mortality. In this group, only one patient died. In this group, many of them died. And if you look deeper, say what are the difference between the group, you will find that one of the group is have a decreased kidney scores over time, and this is days, and eventually reduced to 0, even with some bumpy here. Another group, even though started with the same score, they decrease, and they increase, and they decrease again. There's multiple episodes of AKI here, indicating that these patients may not really stable during these days. So this group has a higher mortality rate as indicated here. So this gives us a hint that when we look at the patient data, we shouldn't just look at the first value or the last value, the highest value or the smallest value. We better model the dynamics. How does this kidney score or creatinine values that change over time? And that could give us a hint about the patient outcome. So this gives us confidence that probably we can use a machine learning algorithm to solve the problem. The first type of algorithm is called the traditional machine learning approach. It could be random forest, supported vector machine, XGBoost, or just different algorithms. And you can see that to be able to use this algorithm, we have to go through a few steps. We're going to have the access the raw EHR data from hospital, and then we do some data processing so that the data being harmonized and ready to use. Then we need to do lots of feature engineering, try to identify which clinical parameter is the most useful for predicting mortality. And this would be back and forth. And then finally, we can make prediction for the patients. So you can see the traditional machine learning is only here, but needs a lot of steps before that, before this prediction to make it work. Deep learning algorithm take a different approach. It just say, give me the data, harmonize the data. We'll just use the end-to-end learning. That means the data, once it's provided to the model will try however method and to harmonize, to mine it, and eventually would provide a rolling mortality prediction. So here we develop an algorithm called the knowledge graph guided double attention LSTM model. Sorry. And we use a knowledge graph, what's called in short is KG, to guide the learning process. Because we know that in the data, there could be some bias in it, potential bias in it, but we don't know what are they. And there could be many, and they're very difficult to identify in the first stage. So we wonder whether using knowledge graph, we'll be able to mitigate the bias so that we can better model patient outcome. In this deep learning algorithm, we obtain a 2D attention in both time and the feature space, so that we will know that whether there's any time-related pattern, the temporal patterns, or there's any relationship between different clinical parameters that can work together to predict the patient outcome. And then when we make predictions, we don't just predict the final stage. Instead, we do a rolling prediction, which can be shown here. So this is just an example of one patient's data, from beginning to the end. When we receive this data, we truncate data to different time frames. They can be long or short. We let the computer do this randomly. So you can see for the first example, we have the time point, the first time point here somewhere in the middle. It could be for the 3 days. And then we ask computer to predict what would happen in the next 24 hours or 48 hours for the same patient. But we also get some samples, overlap samples from the same patient and this one as well. And all those will be used as a training data for our algorithm. The second phase is to extract knowledge from the knowledge map. So here is just the knowledge map represented as a ontology. It's basically this root node means everything. And then we can go deeper and deeper to very detailed knowledge. We extract the knowledge banding, and then we put all this knowledge group together to form a KG group. And we compute the distance between the KG and the embeddings. Now we have the raw data being truncated to different time frames. We have the knowledge map that can be modeled with the KG groups. Then we can finally put all the data together into a deep learning model to predict the patient outcome continuously. So you can see the first part here, these are the features. So usually the dynamic features that measure, over, for example, creatinine values that measured over time, the fluid balance. The static features are patient demographic information. For example, the gender and the age. And this data will put into different groups and based on the knowledge provided. And then each group will be trained separately using an LSTM model from first time point to the last time point in their own sample data. And all this outcome of STM will be put together using feature embedding. Then we compute the time attention and the feature attention with all these LSTMs and generate a double attention guided by the KG group and finally make predictions. I know this could be lots of jargons here, but this basically is how AI algorithm works. It has to rely on lots of data here and also some knowledge that can guide the grouping of the data and guide the computation of the attentions to get a better performance. When we have this knowledge map, I just want to show you how exactly we extract concepts. For example, we have a term called the heart rate. Okay, this is very often shown in our EHR. And then in the KG knowledge map, for example, human phenotype ontology, there was a term called abnormal heart rate variability, which was here, so that we can associate this term, the values in this term, with this concept. So it's a one-to-one mapping. This could be the simplest case. A lot of times we have a term, we have multiple matches in our knowledge map. This is the example. The systolic blood pressure was a term in our EHR. And then in the KG, we can see there are two opposite two things. One is called elevated systolic blood pressure, another decreased pressure. So those will be the two nodes. And we know that these two are pointing to the same term here. So these two terms will be combined. So we just apply some very general rules to make sure that this knowledge map can be used for different diseases. For EHR terms that can be matched to one concept, we just directly use the corresponding concept. For EHR term can be matched to multiple concepts, then all these associated concepts, no matter where they are in the knowledge map, are going to be extracted and used as a whole group. Now we have these EHR groups. The next step is to learn the concept embedding. We use an existing tool called Chen's E to generate embeddings from the graph. Basically, it just traverses the network and find out the best representation of the nodes in the graph. It's energy-based model that's also very widely used in knowledge graph embedding. And then we can group all these concepts based on the terms issued in the last slide, and we can generate these concepts is all together because they represent the same term, and we compute the distance of the terms. Just to show you some examples, we grouped for the AKI patients. The left side of the concepts, the systolic blood pressure, the heart rate, creatinine, potassium, sodium, all these concepts. And on the right side, they are grouped into concepts like cardiovascular disease, metabolism, blood, respiratory. And when you put all this data in a 2D platform to visualize, and you find that the terms that in the same group are put together. So that means they are naturally associated with each other in the knowledge map. Now we have the data that can be represented in a time pattern. So for example, this blood pressure, the value in the first time point, second time point, and all the way to the last time point in a time frame. This is heart rate, have all the values. It could be many values, it could be hundreds of values included here. We have this, we use a deep learning model called long short-term memory to model this dynamic data. And each of these LSTM layer outputs the hidden status here, hidden status of each group, and they concatenate all these hidden status into one status. And based on that, we go two different directions. One is the traditional way, we'll just go to the transpose whereas here the transpose and activation and the max and get the final outcome. Another is that we transpose the matrix so that we can study whether the association between these different clinical parameters and see how that could eventually affect our outcome. And this KG, the knowledge map guiding, was almost everywhere. Include the input, we have the terms being grouped together, and also here the KG we used to introduce to help to harmonize the double attention. Okay. In our experiment, we studied the AKID patients, as we said. So here we have 600 AKID patients from UK healthcare, and also use a public database, which is Mimic3. We extract 170 AKID patients. We use a human phenotype ontology as a knowledge map. And here we focused on 12 temporal features because those were mostly related with the AKID. They include systolic blood pressure, systolic blood pressure, creatinine values, bicarbonate, and so on. So all those parameters of the data are extracted from the EHR data from UK and from Mimic3. We also include 6 static features. They are basically the age, race, gender, admission rate, BMI, Charlson comorbidity scores. We detect 3, also have 3 flag features. This is just a yes or no. That means is a patient on the CRT, is a patient on the ICU, on HD, or the patient is in ICU. So all those features are included in this model. Of course, if we study a different disease, you will have different clinical parameters. Then we have to retrain the model and see and how the model performance will be look like. Here we predict the mortality in the next 72 hours, 48 hours, and 24 hours. This is the data we provided. And we have small number of patients, let's say 600 patients, but when we break down the patient record into short time frames, we can actually boost our training data. So you can see for the UK data set, we have about 12,000 alive training, and then have 2.6 thousand death data as training. So for the 72 hours, we have a similar number for 48 hours and 24 hours. This mimic 3 data is a little bit smaller. So in the 72 hours, we have about 2.7 thousand training for live and 390 for deaths. We compare our model with the traditional machine learning model like random forest, XGBoost. We also compare with classical deep learning models, including LSTM and the transformer models. Instead of simply comparing with existing models, we also conduct an ablation study. So here we say, what if we only use the time attention? What basically means we forget about the correlation among these clinical parameters. We also ask if we use both time and the feature attention, but forget about the knowledge graph. Let's let the model learn from raw data, what would happen? So all those are these algorithms we want to compare and figure out which part of the model is important. Here we show results on the UK data set. The first figure is results on the 72 hours, and the bottom figure is for 48-hour prediction. In both settings, the patients are on RRT. So you can see for the XGBoost model, it doesn't really work well. The performance is also around random here. It does not really show a good performance. The STM model is better than random, but still the performance is less desired. Transformer model is more complex, so we expect to have a better performance here. While our model issued in the last row has significant better performance regarding the AUC, accuracy, precision recall, F1 scores on this balanced data, and also achieve a higher score on the unbalanced data set. So this is for 72-hour prediction. If we narrow down the window to 48 hours, the problem becomes tougher, and so you expect that we'll have a low performance. But still, you can see for our algorithm, we achieve the good performance comparing to the 72 hours. So that's also the model performance better than the traditional ones. And also compare with our ablation model, which we can show that the clinical parameters are not alone. They have to be correlated to better understand the patient. And the second was the inclusion of the knowledge can reduce the uncertainty of the model so that the model performance was improved. You can simply look at the AUC values. So this is the one without feature attention, and this is without the knowledge map. They are not as good as our models. So although this is only 1% increase, but if you look at the ACC precision recall, the performance, if you will recall, the performance increase is about 10% here. But we also show some case studies to better understand the data. So this is one survived patient. You can see that the model predicts the patient have high risk, so 75% the patient will die, but then reduce because of the treatment. And then there was a second episode, they're gonna increase the risk, but it was controlled well, and eventually it decreased, and the patient discharged alive. We will look at the attention, and we found that in these attention values, the metabolism, blood, and the respiratory are correlated with each other. The respiratory data is always important, while the blood pressure has some important the values. So if we dig deeper, say, oh, what are these values? How this could be related with our patient outcome? This would be some observation we can make, and we can see. We can, of course, we check whether this is just a single case or it's repeatedly appeared in our data and associated with a patient outcome through reasoning process. While we put all the patients' risk trajectory together, we found an interesting common trend for the survivors and the non-survivors. Or you can see here, when the patients entering the ICU, then the dialysis, they have a similar risk rate. For these non-survivors, they basically they kind of go down. They have increased. They go down a little bit and increase again, and finally they died. And for this group, they have some early episodes here, but then they quickly go down and it's very stable, and eventually they are alive. So this trend analysis may assist our healthcare providers in making early decisions. So that is the first model we introduced. You can see that the idea is really simple. We just wanted to combine the current, at that time, the best deep learning model with the knowledge map and to see how that the knowledge map can help us to mitigate the bias in the data so that the model is going to make a fair prediction. The second model we developed in this same manner is still on the same direction. We want to use the knowledge map. The only difference is that we're not going to use a knowledge map just around the deep learning. We actually want to use the inside of deep learning models. So that's why we develop a different a deep learning model. This is totally different from the first one regarding that how this knowledge, this all represented knowledge was incorporated into the LSTM cells, where you can see that these cells, this is the patient physiological status data, and this was the knowledge graph. They were used to control how the message was passing from the previous time point to the next time point. And we found that if we can do it this way, we actually could achieve a better performance. So as we showed here, the last row is our method. This is basically on the same data set. So I'm not going to introduce the data set again. So you can see that we achieve performance 72% ROC and the highest F1 scores and others. We also extend our comparison to other deep learning algorithms like a phased LSTM that can address the non-regular type sampling data problems. The return model, the TAM model, or developed based on LSTM to address the clinical problems. So still we see that our algorithm achieves overall the best performance. So this was tested on the 1 versus 1 data set. This is the balanced data, this is 1 versus 9. That means in 10 patients, 1 of them died and another 9 survived. So this makes the problem harder for computer to study. And you can see the XGBoost basically failed, but our algorithm achieved, even though that you see the scores is low, but it's already much better than existing algorithms. We just don't just stop there. We also want to ask, can our tool be fair? That means if we model can make a good prediction for one subpopulation in the whole data set, can it also occur equally well on different populations? So we just use the EHR data and just do a clustering algorithm to divide the data into multiple classes. And then we ask, how does our algorithm work on different data sets? So overall, you can see still our algorithm achieves the best performance when comparing the others on different subpopulation levels. Or the level 1 means that we just cut the whole population into 2 pieces, 2 groups. The level 2 is 4 groups, and the level 5 is even deeper, many small subgroups. So we expect that when we have smaller subgroups, the deviation could increase and overall performance could decrease. But still you can see our model achieve the best overall performance among all these settings. So this gives us a hint that the knowledge map itself is really powerful. If we use it well, either inside of deep learning models or surrounding it, we should be able to get a more robust algorithms that could be suitable for clinical use. So that's just a part of the work. The other pieces of work was related with another philosophy, which means if we have a model work very well on one data, on one population, does it also work well on others? It's very hard to say because the population could be totally different. And the data could be, the concepts could also be different. So it's hard to just say, okay, now we binarily say the model trained on one place could also work on other places. So in the literature, there will be two different opinions to address this problem. So one algorithm is called domain adaptation. So that means we will let the model to learn hidden features that are indifferent across domains. So basically the model will forget about it. So you can see in the input, we have data coming in to the model. And then finally, we have a domain classifier here. It's about whether this is a male or female, is a senior or just adult, and there's other status. But we said, okay, in this approach, the model simply will forget what they are. And then we'll say the model will be robust because the model doesn't care about this variance. Okay. On the other side, there's other kind of algorithms called the domain-specific bias correction approach. This approach tries to train multiple candidate models for different demographic groups. For example, we have patients from South, patients from North, patients from East, from West. Each of them will be fit into different models, one model. And then finally, we'll decide which model to use based on where the patients are from. So you can see these are two strikingly different approaches, but they both show to be useful in mitigating the data distribution shift problem. So in our last algorithm we put here, we say we don't want to let decide which path should choose. So we just let the model decide by itself. We put the domain loss here and let the model to learn which parameter or which strategy the model will choose for different parameters. And then we put a domain-focused representation here for the patient outcome prediction. So when new patients are coming in, we'll first ask these different domain classifiers, the male, female, the gender, the race, the gender, the age, so that we will know something about the domain classifiers. And then we use this dynamic weight that I learned from here to decide which of these specific models, deep learning models, going to be used for final outcome prediction. So you can see in our settings, both the domain adaptation approach and domain-specific bias correction approach are two special cases. Well, we just wanted to let the data model learn from the data. So we develop algorithm, and again, this was a test on the AKID patient cohort, and you can see we achieve a better prediction results comparing to traditional machine learning models. We also say, okay, since it's a good data representation, can we also test it on different deep learning algorithms, non-deep learning algorithms? Again, you can see that even say we just use random forest support vector machine XGBoost, but we combined with our data, unbiased data representation, we can achieve a much better performance than those traditional algorithms. By the way, I would say that the last three measurements, the DPD, EOD, and the EQOD are fairness measurements. Those scores are lower the better. So when you see this 0.09, that means that the model is really fair on different subpopulations. While 0.18 basically means the model is biased to certain subpopulation. The ablation study also showed that all those components we incorporate in the model are useful for making final outcome predictions. This is an interesting figure that we just found recently. The x-axis is the domain loss. So basically you want to achieve a good domain loss. It means the lower the better. While the y-axis is outcome loss. So the one outcome is, say, do we predict the patient die or patient survive? So if we make a good prediction, we should have a lower outcome loss. So you can see sometimes they compete with each other. And then we put all this data together, we see two opposite patterns. This is for the age. So you can see when the domain loss was lower, this age loss was high. That means the model simply saying that we forget about the patient's age distribution. We can't really predict the patient age well. In that sense, we can predict outcome better. So this is domain-invariant approach. And this is another one, it's a CVD. And you can see that when the domain loss was lower, the outcome loss was also lower. So indicating that this is domain-specific approach. The model basically automatically pick up the strategies for different clinical parameters to decide how they can be used in the model to make final predictions. So in summary, We know that integrating knowledge graph and the deep learning model are powerful. They could enhance model prediction performance. We could integrate the domain adaptation and the domain-specific bias approaches, which also lead to better understanding of the relationship between the EHR terms and the patient outcome. So our work may eventually enhance the capability of using EHR-based data for assisting timely clinical decisions. This project was supported by my NSF grant and the NIH grant led by Dr. Javier. This was a few publications of this work. Okay, so we talk a lot about so you can see that we talk a lot about the EHR data and how this EHR data can be used. But what I didn't really say is, how do we get the EHR data ready? How can we make sure that they'll be useful for the following studies? So I'm not an EHR guy, so I'll just show you how did we harmonize CT images to make them useful for the future, for the patient outcome study. This was the CT imaging, and at the time of 2014, 2016, people start talk about how should we read the CT images. We're not really satisfied by simply looking at the volume or the location of the nodule. We actually want to look at the texture features. But when we look at texture features, we found something inconsistent. See, here is just the same phantom, the same tumor, but we scanned with 3 different acquisition parameters. This was same tumor, you can see here. So texture feature is the same for the same tumor are totally different from each other. This was more homogeneous. This is heterogeneous. It's somewhere in the middle. So if you measure the texture features, no matter what method we're going to use, you will get different outcomes. The thing is, when we see these results, can we tell this, the texture feature is really related with the patient outcome was actually driven by how we use the CT machine. So you can see there's a challenge with the non-standardized images. The image feature could vary, and this variation could hinder the progression in patient personalized medicine. The machine learning models, if we train them with one CT machine, CT image data, may not work well on the others. The radiomic feature models are highly dependent on the radiomic features that was changed from one to another. So to that extent, we defined a procedure to standardize CT images. The idea is simple. So giving a non-standard image, no matter what it is, well, can we make it standardized? It's not just a number, this is an image with lots of pixels here. So we want to make a full use of the generative network in a deep learning area, and then we can see if we can synthesize another image, just basically redraw a new image. And so the redraw the image, because the synthetic image is closer to the standard image. The first thing we need to do is to create a database available for training our model. We use a long band chest phantom with 3 artificial tumors. We scanned with GE scanner, Siemens, and the Philips. We have to ship the phantom around the nation to get it scanned. We use different corners, slice thickness, KVs, different combinations. Eventually went up with about 35,000 image slices. And for each image, we extracted 1,400 radiomic features. We develop a standardization workflow. So we're gonna not just check whether the quality is good or bad by our radiologists in the end of the process. Instead, we have many intermediate steps to check whether this is soft tissue, how does soft tissue look like, do they overlap a lot, are they fake or real? And then we have all the artifact check in the middle to ensure that the data we put together has high quality. We use a pre-trained model because even though say we have 35,000 images, still to train a neural network model, we need a lot of training data. So we basically make full use of pre-trained BGG and the ResNet to model image distributions. This is our first model. In fact, this is our second model, published in 2021. These boxes are fixed model and the trained model. So you can see they will blend together to be able to make a full use of the pre-trained structure, but also our images generated with our scanners. We adopt a window training approach because the city image has a very wide dynamics. If we simply focus on 0 to 256, we're not going to cover the whole range. We need to go way beyond it. So we use a fixed growing windows to grow from the low end to the full spectrum. And then we use a dynamic approach to focus on those areas that the image quality was low and enhance those areas. We compare our algorithm with existing approaches. And this is our 3 algorithms, the first algorithm, second, and the third. And this number indicating how many radiomic features were covered using our method. So the number is higher the better. So you can see the last column here, this has the highest values. These are 2 different variations of algorithm. This is our older algorithm, this is another older algorithm. These 2 algorithms developed by other groups. So just to show you a result, you can see this is the input image. It's like this, and our target is here. That means this is the standard image. It's the input. We need to regenerate the image based on the input so that it looks similar to the target. Well, target is unknown, of course. So this is one method, the second method, and this is our last method. It does not look exactly same as a target image at the pixel level, but it's a heterogeneity. All those texture measurements are very similar to it. The trick is we don't know the target image, right? But still we need to let the model learn how this target image can be generated. Okay, so those are different algorithms we developed. Due to time, I'm not going to go to details about the deep learning algorithms, but overall, the message is that we keep improving it. We want to get a better performance. We can do cross-scanner image standardization. So our work is not just we're not just sitting there waiting for people to get the data ready for us. We actually step into the standardization procedure and they try to do the image standardization, which is really hard to do it manually. We have a general framework, and this general framework includes all our algorithms developed so far, and it showed that the final algorithm here get a better performance comparing to the original algorithm we developed. So we keep improving and keep getting better and better results. So we built, first of all, we built a database with more than 35,000 image slices. We developed 5 image standardization algorithms, and this work was supported by NIH and Kentucky Lung Cancer Research. And those were the publications. That's we work on this direction. I would like to thank my current and former lab members. So Dr. Sajed has graduated last year. He is now postdoc at Stanford Medical School. Dr. Chi has graduated also last year. He is now postdoc at Cancer Center at VCU. Lucas and Salim are the 2 persons who developed the algorithm we showed today. They're going to graduate next year. They're on the job market. So if you're interested in their work, please contact with them. I have 2 new students joining me earlier this year. Dr. Isaac will work on the cancer-based, case-based research, and Chen will work on medical imaging. I also like to thank my collaborators. Javier was really not just a collaborator, but a friend, introduced me all these concepts and get data ready and support our research. Dr. David Kramer is my mentor at when I was assistant professor, and the GQ-san who hired me to UK and opened the door of medical informatics. So really appreciate their help. Thank you for joining my talk. I'm open for questions.
Thank you, Dr. Chen.
Yeah. Okay,
that was wonderful. No, as you said, that was really wonderful and a great exposition of what you've done so far. So yes, absolutely. We have a few minutes for questions.
Yeah, I have a question. I also enjoyed very much this presentation. We struggle, with our models with overfitting. Do you have some recommendations, how to address with this sort of EHR-based analyses, how to address the overfitting?
Yeah, overfitting is a long-standing problem, and there's several approaches to work on this. But basically, we found out when the model start to overfit, and then we just go back one step, because that was the breaking point, right? That's just a step before the model is going to overfit. So probably that's the best time we should stop training the model and use it. So this is one approach. Another approach is meta-learning. It means that you don't end up with one algorithm. In fact, you have, say, 5 or even 10 different algorithms. They each will give you their own independent answers. And your answer, the final answer is the vote or a weighted vote of them. So that if one of the models is overfitted, our model still can rescue and get the correct answers.
Thank you.
I have a question about knowledge graph. So how many nodes and edges are in your knowledge graph? Are they weighted edges or just directed, undirected? And also, how did you develop this knowledge graph? So did you collaborate with some clinicians, or so that's my question.
Great question about the knowledge graph. We use existing knowledge graph called the human phenotype ontology. It has thousands of nodes in it. Basically, it measures just about the patient physiological parameters and how they are related with each other. We directly use it because this is well built and being widely used. But if you are more interested in bioinformatics, there's also gene ontology. They just if you're interested in drug, there's drug ontology. They're just different ontologies for different kind of studies.
I guess I have a really naive question. So, I mean, is this work moving into the clinic? I know that's the ultimate goal, but is there any of this already being piloted? And like, how far away are you from, implementing some of these and changing, clinical practice?
That's a great question, Kelly. I think in fact, there's lots of obstacles there before a model, an AI model can be eventually used. And we are still exploring. Right now, our purpose is to test whether a model that is useful for one disease can also be used for another one. For example, if the model is good for AKI recovery, can we also use it for patients with PKD? So those all related with the kidneys. They have a similar measurements, similar tests, but the targets is changed. So we expect that the model should work on that. I believe that if we have a broader applications, the model will be easily to be adopted into clinical practice.
And if you allow me, thank you for the very nice talk. I think implementation, right, is where we struggle, because we always try to find the most accurate model, but we don't develop. While we try to improve methodologies to develop the models, we lay behind in testing the concepts that the models are trying to resolve, right? Like how to use them. So if we keep waiting for the perfect model to then start testing implementation, then probably all of us on the call will not be here when somebody will test it in the future. So I think that's, my question to you, Jing, is what's the perfect ecosystem for this work? How create these platforms where clinicians, scientists, clinicians, and also incorporating other stakeholder feedback can come into this work that is very innovative. But in my learning in a slow pace of these machine learning algorithms, I found a lot of computer scientists that have no idea of the application, how this could be applied. I mean, they know that the model is very innovative, but they don't have the clinical concept to move it to the bedside. So how we can create these ecosystems, like where we can work together more effectively?
Yeah, definitely, Javier, this is a great question. I think these two teams should unite. We should bridge the two teams so that we have a shared culture. We understand the problem on each side. For example, for deep learning or any algorithm, we need to understand this boundary, when we should use it and how are we going to use it. Just like patient inclusion criteria we often use in clinical study, the algorithm needs that too. we need to set a boundary for it. We can't say this tool is useful in all cases. That's impossible, and that's too challenging. So if we understand each other better, I believe that eventually we're able to deliver to, and also as you said, the tools improving, the data is expanding. We can't wait for another team to make it more perfect, right? We not have to work together from now to solve the problem.
Great. Well, I just wanted to thank our guest, Dr. Chen, for a wonderful talk and really exciting and research on the leading edge of many things we as clinicians think about, but also as informaticians. And appreciate everyone's attendance. And we'll close out this session. So thank you again, Dr. Chen.
Thank you.